Three, two, one, and we are live. Hello, everyone. Welcome to 345 Tech Talks. And in today's episode, we are talking about, well, this is episode 3, Revenge of the Sith. Actually, no, it's not, is it? It's episode 3, Fundamentals of Kubernetes. So, as usual, I have with me Paul Brown. Paul is Chief Engineer and CTO of Glue, and also co-owner of 345. I'm Andrew. I am the CEO of Glue and a co-owner of 345, and we're about tech. Now, I've got a little bit of housekeeping first. Last week, I was really happy that when we actually had our tweeted out our podcast episode. Obviously, Paul can't see this. But when we tweeted out our podcast episode, we had a reply about how you pronounce ScyllaDB, and I'm just going to quickly play this now. Hopefully, this will come through.
Your project name? I pronounce it Scylla.
Scylla? Wait, I've heard Scylla. I've heard
Scylla, Scylla, Skyla. I've heard a couple of engineers pronounce it Scylla.
Scylla?
There you go. That's enough. But we obviously have been saying ScyllaDB, and there are enough people that were saying ScyllaDB, which to actually make me feel like we're justified in using that.
We just sort of made it up, right?
we made it up, and we kind of sort of thought, well, how would we do that? But it's really good because
intelligent guess.
Because what they should do is a bit like Capital One and that sort of thing. They should produce an executive edition of Scylla and call it Black.
Oh dear.
It's one of those days, I know.
One of those days, yeah.
It's one of those days. So the moving swiftly on. One of the things we talk about when we talk about software, we talk about the 7 outcomes. Now, I was really kind of remiss last week because some people listen to this podcast just in the, and some people watch the video on YouTube, and I just rattled through the 7 outcomes, assuming that people were looking at them on the screen without realizing that people might be listening to it just on audio. And it's a bit like that old snooker commentary where it goes, for those of you watching in black and white, the blue ball is the one behind the pink. It's a bit like that. So I will actually talk through the 7 outcomes, and then we talk about the ones that are particularly relevant. So with our approach to delivering software, we look at 7 outcomes for success, which are rapid delivery, quality and bug-free, available and scalable, secure, functional and lovable, costs are optimized, and we're standards compliant. So those are all the things. And when we talk about Kubernetes, there are a number of the 7 outcomes that are the ones that are particularly relevant to us. So as we mentioned in episode 1 with Kubernetes, where people go for Kubernetes because once they've got it set up, it does facilitate rapid delivery. It really helps with making your systems available, scalable, and it really helps with optimizing costs, the hosting density, and the way that you can achieve failover in a very cost-efficient way. So those are big, the big points, and certainly relevance for us. This is what we're building as effectively the whole of our Glue platform on. So we are building that on microservices. So all the stuff we are talking about today is really what Paul's engineering team has got in the garage right now. And this is the technology that we for our stack right now. So with all that really long intro, fundamentals of Kubernetes. Where do we start, Paul? Do we start with really microservices and the benefits of quick recap on microservices and how containerizing them actually a good place to start?
Yeah, why not? So Kubernetes is, some people see it as a microservices platform. It's really it's a container orchestrator tool. And if you think of a microservices architecture as being lots of discrete, small, focused services that perform a specific function, and a collection of those services is the application, right? But I mean, the key thing with the microservices approach is that each service is independently deployable.
Yep.
And independently scalable. So you're going away from the monolithic approach to building applications, where application upgrades are an all or nothing approach. And we know how well they go sometimes. So
and scaling is an all or nothing approach.
And scaling is an all or nothing approach. And obviously over time, there have been changes in the way that applications are architected, obviously client server, and then you go, three tier, so that you have a separate scalable business logic layer, and then N tier. So it's already starting to split the application to make the application itself easier to scale, easier to deploy, but each of those tiers are still somewhat monolithic, right?
Yeah.
Whereas microservices, I think microservices really work now in the days where we have very fast networking.
Yeah. Just rewinding that just a second. When you were talking about N tier, one of the things you used to get is, you'd have your web servers that are serving the UI and that sort of thing a lot of the time, or it might be a thick client. And then you'd have your app servers that you put your web service. But generally, you might have an app server, and if you had 10, 20 web services, you stick them all on all of your app servers, and that would be and that would kind of be your middle tier of your kind of architecture, and then you'd have your database server set behind it. And when we're talking about independently scalable, what we're saying is that the fact that previously you might have just added more servers and installed everything on, and that meant that, and that had a few knock-on things. I mean, firstly, you're scaling everything, but you're not scaling them independently. But also, if there are dependencies on one service, then generally those bleed through into the other ones because they're deployed in the same machine, so the same versions of the underpinning sort of software apps that they're using. And the software versions kind of bleed through from one to the other. So if you're changing one of them, you'd have had to have changed the other ones, and then suddenly what becomes a minor bug fix in one service suddenly becomes a massive regression thing, affects everything else, and that's what we're trying to get away from. And what we're trying to get to is where, if you want to make a change to one thing, you change that one thing, you redeploy it, and everything else carries on and is happy. So, does that sound fair?
Yeah, it does actually. I mean, it is a good point. I think we sort of briefly touched on this in one of the other episodes, but you're absolutely right. It's the cost of regression. I mean, hopefully, everybody understands the benefits of automated testing. But even so, if you've got a very large application, then the cost of regression can be quite high, even if it's automated. So the being able to being somewhat pragmatic about the way that you regression test changes, so that you fully regression test your changed microservice, and then you run a suite of almost end-to-end or scenario tests over the whole platform to make sure that that service that you're going to deploy individually still works in the context of the wider application.
Yeah.
But you can imagine that that's a different prospect compared to regression testing an entire monolithic application.
Yeah, I mean, especially if you've updated a framework on one of your applications, and then suddenly that framework has to be tested against. Yeah, that's that sort of thing is, and that's why containerizing helps, because containers isolate that application, and it makes it look like it's got its own isolated little operating system. Even though multiple containers can be run on the same machine, you don't get the bleed between them.
But crucially in that I mean that's a good segue into containers. But crucially, that each application might have its own dependencies on certain software libraries and so on. But what you don't. So the nice thing about containers is that you encapsulate all of that inside that container. So if you go back in time in the way that we used to deploy applications before containers, you may have a number of different components that require different software on that machine, and then making sure that machine is configured correctly with all of the dependencies that all of your components need, and making sure that those dependencies work together, and any upgrades to those dependencies don't break other dependencies, don't break your components, and so on. And it becomes a bit of a minefield. I mean, DLL hell and so on. But it was a real problem. And so you had configuration management solutions like Chef and Puppet and so on. But they're fundamentally sort of.
They didn't fix that problem though. I mean, they kind of at least made sure that you had a consistent state.
Exactly. So the sort of desired state configuration approach, but it's
and that is a good thing, but it's not fixing the bleed of dependencies between applications.
Exactly. And the configuration management approach is I think what do they call it? It's mutable infrastructure, where over time you get configuration drift, and so therefore you end up these small little problems just creeping in. And
where I mean, a typical one of this is an operator logs on as an admin and tweaks a few settings, and then on one server because it's not quite behaving, and then before you know it, as 6 months down the line, suddenly every single server is wrong.
Yeah,
because you've been doing that.
Yeah, so it's definitely a real problem, and containers go some way towards solving that, where you build your container with its dependencies, and that is isolated from other workloads that are also running in containers, and you keep in a way your host machine that is running those containers can be fairly lean, right? It doesn't actually need to have too much in the way of support other than what the container, like Docker, for example, what Docker needs in order to run, and for those containers to be able to network and talk to each other and so on. So it's you can end up with a very sort of slimish host operating system that then runs containers, because all containers are equal in a way when they run, but the sort of unique dependencies that the application services have within those containers are encapsulated within those containers, and that is from a sort of operational sort of system administration perspective, that's big, because you just take away all of those little niggly issues that you might get from trying to maintain a consistent set of dependencies on the machine. You just take all of those issues away.
Yeah, and that's it's almost like hard to understate how kind of important that is, because it's I mean, we spent years grappling with all this, didn't we? So it's so actually to have arrived at the point where we've got a solution for this is really good. The thing is, and this kind of comes next onto Kubernetes, is that you can go onto Docker Docker's site, download the Docker runtime, follow through the examples, and within 30 minutes you've built a container, put your app in it, and it's like, yeah. But to actually get that container, get that concept of building containers, because your devs can start building containers, and they can do that quite quickly. It's ultimately a very small delta on top of building, building their API or building a service. But actually, to take containers and to have a containerized architecture that runs in production properly isn't a trivial task. And I think that's where people get. I think that's where people struggle with Docker. Is that the leap from I built a container to I've got a microservices architecture running in production is actually a lot of work, and so that kind of brings us on to Kubernetes, which is a technology for doing this. But you want to just talk a little bit around how in your mind you go from the container to actually the leap of I need to put together an architecture, and this is what it looks like.
Yeah. So, well, if you think about just a runtime, so you've taken the decision to go down the container route because it makes your life easier when it comes to things like dependencies and so on, and so you end up with a sort of homogenized view of units of execution that run on a machine. So very thin host. All containers look equal. In terms of execution, they all roughly look the same. Yeah, so that's great. Now the problem is that if we talk about availability and scalability, you're not necessarily just going to run one machine in your production environment, right? It's where you run.
You can't have availability with one machine.
Despite how many processors and disks and power supplies and things like that you might have. Yes, exactly that. So when you run a Docker container, you're interacting with Docker on a machine to run that container.
Yeah.
Now, if you want to have a scaled out, so let's say that container contains a web service, and you want to scale that out, so you want to run multiple replicas. You're going to need more than one machine to run that. So then, how do you coordinate when you say I want to run my web service container? How do you coordinate deploying that container to all of the different machines that you want that container to run on?
Yeah, and like you said, if you've got the whole thing of independently scalable, so if you've got 20 different microservices, each own container, and you need to independently scale one of them, how do you do that?
It's if you just start at the beginning, like placement of containers. If you've got one container, but even just two replicas, then you've got to think about, okay, I need to Docker run the container on one machine. Now I need to go over to the other machine, do a Docker run, and so on. And it quickly becomes, particularly microservices, where you break your application domain down into lots of discrete functions. It becomes untenable to take the approach of manually placing and running containers on different machines so that you get the balance of resource usage across all those different machines with all the different containers. Now, obviously, if a container dies, then Docker will restart it, provided you have the restart flag on it. Yeah. So from the point of view of an individual machine, then you've got and you can set resource limits on containers in Docker, and so you can make sure that containers don't overrun a machine. And that's all really great. But unfortunately, when it comes to then deciding that you're going to place containers across different machines that all maybe have different resource levels, the sorts of resources they provide. And so all of a sudden you get into this whole, how on earth am I going to do this? Yeah. And so that's where container orchestrator tools come in, because they allow you to express rules by which containers will be placed onto particular machines. And the container orchestrator tool will make sure that, okay, so I've got a container, a web service container. In the what they call Kubernetes manifest, in the manifest, I've said, actually, I want 5 of these containers. I want 5 replicas to run. And then I just tell Kubernetes, here you go and deploy these 5 replicas onto the cluster. And you decide, the cluster orchestrator tool, you decide where you're going to place them best based on what resource, what free resources that I have on each of the machines. And so, you can go much more complicated with that and about how you decide to place, but at the very minimum, it's you're allowing the container orchestrator tool to make that decision for you.
Yep.
Which is, you're just simply not going to be able to do that yourself. And so
not with any degree of efficiency.
Not with any degree of efficiency, absolutely, and constant monitoring, right? So you use a cluster orchestrator tool.
Yeah.
That's the sort of first thing is like, okay, I'm definitely gonna have more than one machine, so I'm gonna have at least 2. And in a microservice architecture, it's pretty likely I'm gonna have more than one type of container, right? I'm gonna have my application is gonna be made up of a number of different containers. And as soon as you get to that point, it's like, well, okay, I don't want to be making decisions about where best to place these things. I really need a tool to do that. So hence, enter Kubernetes, really.
Okay, so Kubernetes, we've already sort of we've unearthed the term cluster orchestrator, and Kubernetes is orchestrator. What does that? And we kind of said a little bit around the fact that it's deciding where to run containers, but what does it actually look like? What does Kubernetes look like when you actually when the software hits the hardware?
Yeah.
What does it actually look like?
Yeah. So obviously, as with any infrastructure level tool, it's never as simple as, okay, I'm going to that machine, I'm going to make that a Kubernetes node, and that machine over here, I'm going to make that a Kubernetes node. There's the software that has to manage the orchestration of, the coordination of placing containers and so on, and making sure that they're running and they're restarted when they fail and stuff like that. So there is, for every node, there's a little bit of Kubernetes software that runs. I mean, it's like a little daemon process, and it's the coordinator on that machine. So it understands what workload it has on that machine. And it's called the kubelet. And the kubelet is just a little process that runs on every, what we call a worker node.
Yep.
In the cluster. Now, worker nodes are where, generally speaking, where all the application workloads run. Okay. Yep. So, but in order to coordinate that, Kubernetes has some other components that assist in making sure that it's making the right decisions and so on. So, and also to allow you to communicate with Kubernetes using an API or using a command line interface. Typically, people would use the out-of-the-box command line interface, which is kubectl or kubecontrol. I don't know. Again, another way of how do people say it? But I always say kubectl. But it's the command line interface to Kubernetes, so you can actually understand what's going on in your Kubernetes environment. Now, the sort of
and that's calling through. Ultimately, that's calling through to APIs that are running on the cluster.
It is, but it's like a different set of nodes, right? So so Kubernetes has some system components that run, and they are they can be containerized as well, but they run on a distinct set of nodes called the master nodes.
Yeah,
you have master nodes and you have worker nodes, and the master nodes are where the system components like the API server runs.
Yeah. And they're the ones that are telling the other ones what to do.
Effectively, yeah. So there's a number of them, but in effect, they run on the master nodes when you use the command line interface, it connects to the API server on the master node, and then the master nodes are controlling the worker nodes.
Okay, so
They're telling they're telling those worker nodes what they need to be doing.
Yeah. So far, recapping where we got to so far. I mean, this is for a lot of people just coming into Kubernetes. This is hard to get your head around. So a cluster is basically an installation of Kubernetes that includes a number of machines. Those machines are called nodes, and we have worker nodes and master nodes. Master nodes run Kubernetes, and effectively, the master nodes are the ones that control all the machines within the cluster, and the worker nodes are the ones that you deploy your application into, that do the stuff you want to do.
In a nutshell, yes, exactly that. So keeping it is most simplest.
Okay.
So when you install Kubernetes, then what you're doing is you're setting up the system components to run on some master nodes, and the kubelet daemon effectively to run on your worker nodes.
Yeah.
So you're provisioning your worker nodes into your cluster, in effect, which involves installing that small bit of software.
Okay. So, I mean, I've got a whole bunch of things here that to sort of work through. So we can either talk about how you might, the infrastructure sides of it, so things like how we attach storage, and that sort of thing, or we can talk about the application side of it, so pods, namespaces, all that sort of stuff. Which one of those do you want to go with first?
Probably the application, I think, because that's the bit that most people probably
are interested in.
And if you're thinking about building a microservice based architecture, then actually really thinking in the application sense. So
yeah,
makes sense to take it from the point of view of the application. Your application from the point of view of you developing. So you've developed some software. It goes through your DevOps process, and part of that process is to produce a container containing that version of that application.
Yeah.
And that container is eventually going to make its way onto a Kubernetes cluster to be run. But Kubernetes doesn't just run raw containers.
It has to know something about them.
It's got to know
how do I treat this container?
Exactly. So you have to have some sort of metadata description about the container and how you want Kubernetes to run that container for you. So yes, it does run the raw container, but you have to provide it some additional information for how to run that container. And that's all expressed through manifests, which are just YAML files, which describe all of the properties for that container. And typically, what you're creating is a manifest that represents something called a pod.
Yeah.
And a pod is a network addressable entity running on the cluster. So so if you think of a pod as being almost a one-to-one mapping between the Kubernetes pod and an application container, that's probably a good start.
Because the thing here is that one of the things that we have typically with Docker is that you want to have these containers running on your different nodes, but you want to be able to do things like load balance between that sort of thing. So the pod is the addressable thing of the pod means you've got one entry point into all of those containers. So, external things talk to running on all the machines, but they all work together as a single as a single unit for application. Is that what you mean by that? Almost.
It's sort of started on services as well there, but so the pod is the description or how Kubernetes is going to run that container for you.
Yeah.
And so part of the description of the pod will be obviously what container is it that you want Kubernetes to deploy. Part of the description will be, how many replicas do you want Kubernetes to run of that container across the nodes. There'll be other descriptions in there, some metadata or rules around can those pods be deployed onto the same node as each other, or does there have to be some sort of anti-affinity rule that says actually you cannot place two replicas of the same pod on the same machine?
Yeah, because again, it's availability, isn't it? That if you want to make sure your app's available, you don't put all your eggs in one basket, because if you lose that machine, you lose your app. Okay, hopefully it'll spin up somewhere else, but you have lost your application then. Whereas if you distribute it across multiple nodes, then the loss of a single node will not be fatal to your application.
Exactly, and so resource limits as well. So you'd express resource limits through the pod description. And so when Kubernetes runs the pod itself is the entity in Kubernetes that gets the IP address. So what Kubernetes really is running is the pod, but within the pod there's an application container. So in order to address the container, what you're doing is you're finding the IP address of the pod in order to be able to address the container. But you express things like, so like in Docker, your web service might be listed on port 80, but through the container, you can't necessarily, if you've got more than one service on the same machine, all listen to port 80, well, they can't. But they can in a container, but you just have to map the internal port into a different external port. So you would do that through Docker, but because you're not interacting with Docker directly with Kubernetes, what you do is you express all of those things through the pod description. Okay. Now it gets slightly more complicated with pods where you don't actually, so there's like a primary container, which is like your application container, but you can actually run more than one container in a pod, just to confuse matters. But I mean, the simplest thing to get your head around is think of, the pod as being the representation of your application container, and the pod represents the rules for how Kubernetes is going to run it. But it does allow you to do some other interesting things with the pod, where you can have the idea of init containers. So you can run a container that initializes the environment, quotes, in advance of the application container running. So, for example, you may, so let's say we've got an application, a microservice that's responsible for a database instance. So let's say a product catalog.
Yep.
So one of the init container might well be a container that when that pod starts, the first thing it does is it checks to see whether the database exists, and if it doesn't, it actually initializes the database and the schema. And so long as that's idempotent, so every time the pod starts, the init container runs and goes, oh, I'm just going to check to see whether my database exists. Yes, it does. Great. Nothing for me to do. But it's something that runs before the application container starts. So you can do a lot of initialization type functions before your application container runs, and that's all part of the pod description.
And why, which I love. Why would you do that rather than your DevOps making sure that database was there?
I guess it depends on the. So I mean, you could do absolutely. So you could do that as part of your DevOps process. If you were running, so one of the techniques that we have in our integration testing environment is that typically you'd have a testing environment where you have your application deployed, you deploy a new version of your service, and then you'd run your integration tests, and it would test against all of the other services that are inside that environment. One of the things that we do with our integration testing environment is we deploy an entire mini application inside, in effect, inside its own namespace. That allows us to run our integration test against a vanilla environment. That means it's always deterministic, because that environment's always set up with all of the right data and so on. Now, part of that will be each instance of that application will need its own database.
Yeah.
And need its own isolated database that is going to deploy the schema into.
Because effectively, if you're running, so if I just play this back, because just to get my understanding of that effectively, when you are in full-on development mode, every single commit into your into integration branch or whatever will trigger a deployment process, and that deployment process takes it takes a certain amount of time to build, package, deploy, and test all that stuff. And if you are unable to isolate each of those, then you end up either with a massive, the potential for all those to be backlogged behind each other, or that you end up with an even worse thing, which is where they collide on the same infrastructure and get non-deterministic outcome. So the fact that you, as you described, means you can effectively parallelize your testing of each without them colliding.
Exactly. And so you could, you're right, you could still take the approach that the deployment of that application could in itself deploy its own instance of its database. But if you think about, it might not be just a database. Let's say it's a Kafka topic. You just want to make sure that Kafka topic exists before the application container runs. It expects it. Now, you could actually put that logic into the application container itself that says, if not exists, create topic, and everything's good. But what you do is you simplify the logic in the application container through taking advantage of the mechanisms like init containers in Kubernetes. That means all of that sort of infrastructure heavy lifting. That's
that your actual app doesn't have to worry about that.
Service that your app doesn't need to worry about.
And then that init container could be built by your DevOps guy, and your app might be built by your app developer.
Yeah, and there's separation of concerns as well, which is another generally good approach from an architectural perspective.
And the fact that your app does one thing, your init does the other, and the fact that you change one doesn't mean
exactly. So the other type of container you can have in a pod is what they call sidecar, where you have, so at runtime your application container is running, but it might depend on maybe a sidecar to do, the classic examples like logging. So that the application itself logs to a little sidecar container, and then the sidecar container is then responsible for logging to, say, an external service or something. So sidecars are not like the primary container, but they're there to support the primary container in what it does. One of the other ones that we have in our Kubernetes platform is so we use Istio as a service mesh for service-to-service communication. What it does is it's really nice, actually. It allows you to express lots of different rules in there for doing things like retries, for doing circuit breakers, and so on. So you don't have to build that into your application.
Because that's the sort of stuff where, in the real world, communications between different components go wrong, and again, you can either build that into your code, or you can have or you can put something in place that does all that for you. So that's what you're talking about there.
Exactly, and there are libraries out there for different languages for doing retry type patterns and circuit breaker patterns and so on. And if you are working in an environment where you are using different languages, then you've got to, I always tend to like to abstract all my interfaces to external dependencies. So even if I was taking an external dependency on a third-party library to do retries or circuit breakers, I'd still have a more abstract interface that my application would be talking to, which would then map onto the sort of third-party library.
Yeah, but and also and that just means, you know, it's just good practice that if you change one thing over here, that you don't break everything else because it's so tightly bound to it. Isn't it? It's just that kind of fundamental good design practice.
It is, but if you think about, you know, that you have to do that for every language, for every retry and circuit breaker library that you use, you know, that's a reasonable amount of effort. It's all got to be tested. If you use a service mesh to do that for you, then suddenly you simplify the logic back in your application container. And you allow the service mesh itself to take care of, you know, network level, you know, the sort of application communication layer, and the things that often break in there. You let the service mesh take care of it. Now with Istio and it uses the Envoy proxy. The Envoy proxy is injected as a sidecar into every pod, and that's how it builds the service mesh. So every single pod gets a little lightweight proxy that handles the network communication between the application container and then the rest of the pods on the Kubernetes, you know, on the Kubernetes nodes. Yeah. So you know, that's another example of a sidecar container running inside a pod. So although, you know, sort of in your mind, logically, you can think of, you know, a pod being a description for how Kubernetes should run an application container. In reality, actually, you can run more than one container inside a pod. But the pod itself is the thing that actually gets is the network addressable entity. So it gets an IP address. Containers inside the pod all communicate on localhost. But externally, other pods seeing that pod will see it with an IP address that's been assigned to it by Kubernetes, you know, by the Kubernetes networking. So pod is like it's sort of one of the fundamental resources, or, you know, one of the fundamental objects inside a Kubernetes cluster, because that's your application workload in effect, in terms of the container workload. And then all of the other types of Kubernetes resources that you can have, they're all there to support, in effect, to support the pods running.
Yeah, because pod is, like you say, ultimately your goal of Kubernetes is to run your applications, and the pod really is your live applications. So here's something. So like you say, you've got your Kubernetes cluster and you've deployed these pods in there. How do they get their configuration? You know, you sort of say, I've got to point to this database. How does it know it? I've got to maybe call another service. How do I know the URL of that other service is? How do we inject all that kind of configuration into a Kubernetes pod or an application?
So you could hard code it. But that's not.
We wouldn't do that, would we?
Right? No. I've seen that before.
But this isn't 1996. Is it?
Yeah, exactly. Anyway, yeah. So Kubernetes has another sort of resource type, which is called a config map. It has another one called a secret, which is like a config map, but it's the secrets are encrypted. But basically what they are the config map and the secret allow you to store data within them, and the data could be anything really. It could be, you know, represent anything within that data part. But typically, what you might have in an application is, say, a config file, which could be a JSON file, could be a YAML file, that you would typically, when your application runs, that it will be provided externally to you. So you'd have a path to your config file inside your container. And what a config map allows you to do is to map the data into your application container as a volume. So in effect, what you're doing is you're externalizing your config. So say your JSON config file, you're externalizing it into a Kubernetes object called a config map.
But does that
And then on the pod description, you map that config into your application container. So as far as your application container is concerned, it's just a config file at a particular location on the disk. But it's all done through this mechanism of a config map and mapping it in as a volume into your application container.
So does that just get applied at the time of deployment, or can you dynamically adjust these things at runtime?
So you can change your pod description. So you could potentially add more volumes. The other thing with the config map is that you can actually change the contents of that config map at runtime. So obviously at the point that the pod is deployed or is run in the Kubernetes environment, then obviously those config maps are mapped in at the point that the container runs, the pod runs. But then ongoing after that, you can go and continue. You can change your config. You can upload a new config map, or in terms of the data content, you can patch it live. So there is a patch command that you can do that you can just patch a certain part of your config in a live environment. It's a fairly well-known pattern that if you want to change config, but you don't actually want to change your application container, then just change the config map, and that just that new config then appears in your pod. I mean, obviously your application has to deal with understanding that config's changed and reloading config and all that. I mean, that's a different problem, but by externalizing your config, you're making that a different deployable unit associated with your application. So you're treating config separate to your application,
which it always should be.
Which it always should be.
And it's been it's been a perennial problem for every type of application. Is how first of all, how do you change the configuration per environment, and then the second thing, how do you dynamically change? How do you make logging more close? Or that's the main one, really. Certainly at runtime is that I've come across. How do I make my logging more verbose if I suspect a problem? Send it back again. So we've got that. So one of the things we almost got to, but didn't really talk about much, is the different types of pods, the different deployment options. So, because we've kind of talked about everything as if it's at the moment like a microservice API, and that's one type of. But we've got so we've got things like replica sets, stateful sets. Talk a little bit around those kind of things and which ones apply to what scenario and how best to do that.
Yeah, so the different types of workload, different types of runtime, isn't it? Where if you have, you think about stateful versus stateless workloads, yeah. So you go back to the client server or the N tier, 3-tier model. Then your sort of middle tier, your application tier always tended to be stateless, right? So it made it very easy to scale. And your data tier was where you had your state. So with microservices, you don't sort of you sort of continue on with those lines, really, where a lot of your APIs tend to be these days web services tend to be stateless. You don't really have a stateful web service. You tend to have stateless web services, which makes them very easy to scale out, to create replicas of web farm style. And so Kubernetes provides that capability in something called a replica set or a deployment these days, where it will literally just create copies of your container across different machines. Okay.
Okay.
And and so you can, and then you can very easily at runtime decide that you actually, you know what, I'm running 5 replicas now. I want to now run 7 replicas or 10 replicas or whatever, and you can make that change on the fly, and Kubernetes will orchestrate creating new replicas. There's no state, so it's very easy to create new instances of that container at runtime, and also scale it back, right? So for when you don't need, you're in a trough in terms of peak load, you don't necessarily need to be running the bigger estate. You could actually scale back in again, dynamically scale in. Now, when the application's stateless, then that's actually very easy to do. But they are sort of service type applications where you would use sort of like the deployment approach in Kubernetes. But then you also have application processes that run more daemon style. So they're not necessarily, a web service is a daemon, but what it's doing is it's accepting external connections.
Yeah, whereas we think of like a worker service, don't we?
Exactly.
Something that just does stuff and it doesn't require, prompting from outside.
Exactly. So more daemon style processes you can represent in Kubernetes through something called a daemon set. But whereas a replica set, if you've got a 10 node cluster and you've got an API service that's in a replica set that with the 5 replicas, then Kubernetes will choose 5 nodes out of 10 to place those replicas. If you have a daemon set, though, what it does is it runs one instance of your daemon on every single node in the cluster. So it's a very easy way to run your application container on every node in your cluster. So, for example, we use that for FluentBit.
Yeah, for as we talked about in episode 1, that's the kind of logging solution.
Exactly. So we use that for local logging. So every pod or every container that runs on that one node only has to talk to its local machine. So it doesn't have to go off box. It can stay on box in terms of getting its logging to FluentBit, and then FluentBit can do the off box process. But you're offloading on the same machine. So where you want to run a daemon style process on every machine, then the daemon set is the type of Kubernetes resource that you want to use.
Whereas if you were wanting to run, a worker service, but that didn't accept external results, but you wanted to scale it and maybe part of your cluster, that you still use a replica set for that.
Yeah, absolutely. And then the last one that you said was the stateful set, and this a stateful set is sort of similar to a replica set, except it's the type of workload that the stateful set represents. And so this is more of a stateful type service as opposed to a stateless service, where with a replica set, chances are you're not attaching any sort of data volume or system volume to the replica set. But with
in a replica set, that's your classic kind of API with a database behind it, where the actual API itself is stateless.
Yes,
that's the typical kind of thing.
Yeah. Whereas with a stateful set, it's expected that you are going to be storing data on a volume somewhere.
And this is kind of where, because we touched upon this in episode 1, where we talked about the hosting the databases. Was this an episode? One of our episodes.
Yeah.
Watch all of them.
Episode 2, maybe, with no sequel. But so the stateful set assumes you're going to be storing data on some volume somewhere. The other thing as well with the stateful set is a lot of the sort of what I would call cluster ready data technologies, where they run in a consensus They're running in a consensus-based replica set. Now, consensus mechanisms like Raft or Paxos or whatever need to have stable network names. So they need to be able to discover the other nodes within the consensus ring. And so they can't do that if the network name is not consistent. So one of the things that stateful sets provide is a consistent network name for every replica within that stateful set. So that means that it's very, very deterministic for consensus-based mechanisms to find other nodes because they'll all have a consistent name, which tends to start at 0 on the end and goes 1, 2, 3, 4, 5, 6, 7.
And an awful lot of the NoSQL database technologies where you add nodes into your database. I don't overuse the word cluster because that's just going to, because you've got database clusters and you've got obviously Kubernetes clusters, but they typically they typically work on the fact that, like you say, you've got a particular mechanism for adding database, and stateful sets support that. So certainly for us, application stuff, replica sets, a lot of the infrastructure logging stuff, time kind of sets, databases, stateful sets. Those are kind of good examples of.
Yeah, so stateful sets provide that stable network identity. They have a particular startup order, typically speaking. Although there's a new annotation now that you can use, which says so typically what will happen is you start replica of 0, and then when that's up, you then start 1, then you'd start 2, then you'd start 3, and forever for how many replicas you have in the stateful set. There is a new option that allows you to start them all, and then the cluster just the consensus mechanism just works out and finds the other nodes, almost all at once. The other thing as well with stateful sets is the volumes that are attached that hold the data for every individual replica are also consistent in the fact that if you lose one of the replicas because you lost a node, and then that replica is restarted on another node, it will automatically find the same volume that it was previously attached to, if it's a network attached volume.
And this is kind of really important for recovering databases, because if going back to when you had physical databases, your machine reboots, but it comes back and it's still got the same hard disk, so it's still got data there. And it's a lot cheaper to boot up a machine, it's got the same hard disk and the data's there, rather than the equivalent to I've now got to restore a backup.
Exactly that. Or in the case of these newer, consensus-based technologies, where they will rebuild a replica automatically, but you're starting from 0 as opposed to starting from.
Yeah, so it's still got to go and get all that data from somewhere and rebuild it.
Exactly, and it's the other replicas that provide that data. So suddenly, now rebuilding a replica from point 0 is fairly, from a cluster and networking perspective, it's quite a costly operation. Whereas if you're talking volume, you're just talking about whatever you lost, whatever you're missing from the point of view, from the point it went down to the point it's come back up again. So stateful sets provide these sort of like deterministic capabilities for dealing with workloads that store data. So similar to a replica set, but it has some particular rules around it that make it very suited to these types of stateful workloads. So those are the main sort of deployment options when it comes to pods.
So we've kind of talked a lot around clusters, pods, deployment, configuration, the deployment options. One of the things I want to make sure we cover, and I know last week was a bit of a mammoth podcast. This one shaping up to be as well. But, so one of the things that is really, be a kind of a big thing in terms of when we look to solve a problem, with Kubernetes. There is you've got to get the technology to hit the metal at some point, and so there's all the hosting options. So some people, believe it or not, even in this day and age, some people still have their own data centers. Although, if you were starting, anyone that's starting a business now probably would. I can't imagine anyone that starts a business now would have their own data. So you then got the cloud options, Azure, Google Cloud Platform, and others. And then we've kind of got what do developers do to make sure they've got something running, and then anything else. So there's a big topic. Where do you want to start on that?
Well, that's the nice thing about Kubernetes, right? Because it can be hosted anywhere.
Yeah, it gives you a consistent experience.
It can be, on premise or in the cloud. And you're absolutely right. You end up with a consistent experience. And which, if you're running, say, on one of the more proprietary container platforms in the cloud, maybe, then, it's, although you have containerized workloads, it isn't just, as we've just been talking about, with container orchestration tools. It isn't necessarily just about the container. It's also about the stuff that goes around it to make sure that can be run in an environment. And so it sort of makes sense to use Kubernetes because it can be pretty much deployed anywhere. So you running Kubernetes in the cloud and then deciding that actually, I'm going to change the environment in which I run my Kubernetes workload. I'm going to now run it on premise. Chances are, it's just going to translate particularly easy, relatively easy.
Well, one of the things there is particularly the other way around is a lot of organizations that have got a massive investment in data centers might say, I want to build my app and run it in my data center now, but we have plans to migrate to the cloud. And so you've kind of got that migration path straight away going there. And the other thing is that a lot of people we work with say, okay, we might be going with this cloud vendor for now, but we don't want to be locked in.
Yeah, vendor lock-in. Yeah.
So we want to avoid vendor lock-in. So what can we do so that at some point in the future, if we have, if another cloud provider becomes, so commercially attractive to move to that we've got, that we want to move, then Kubernetes gives you it gives you a real kind of edge in all those scenarios, doesn't it? Because your application should be able to cope with that.
Yes, absolutely. And vendor lock-in is a lot of people have a real fear of vendor lock-in, right? So that they want the flexibility to be able to move easily enough without there being too much disruption. I mean, there's always going to be disruption. If you're going to go from one cloud provider to another, there's always going to be some level of disruption, but you can minimize a lot of that about the approaches we were talking about in terms of abstracting all of our external dependencies, even down to code level, abstract, and that just makes it, much easier to isolate yourself from the sort of external changes that happen. And Kubernetes is another way of abstracting. So Kubernetes provides, quite a lot of sort of hosting support out of the box within different environments. So you can run Kubernetes in the cloud. So let's say AWS, you could spin up all your own EC2 machines, and you can then deploy Kubernetes manually yourself. So you can run the master nodes yourself. You can run the worker nodes yourself.
Would you ever want to do that?
You're still running in the cloud. I personally wouldn't. So we're using EKS, which is Amazon's Elastic Kubernetes service, which what they do there is they actually run the master nodes for you.
Yeah.
So they control the master nodes. They make sure that they're highly available, scalable, and so on. and all you have to do is you run your own worker nodes and you attach them into the cluster.
And those are EC2.
They're just EC2 machines with a particular image, particular EKS optimized image. But otherwise, they're taking the headache away. So it's sort of a partially managed service where they're taking the headache away of making sure that the masters are always running for you.
Yeah, because the master gives you, like we said right at the start, the master gives you your cluster.
Exactly.
It's then how much you put, how much you add to that cluster.
Yeah. So you're getting some of the benefits of the cloud hosting with the managed service, but you're still running a workload on it that has no real vendor locking, because you could migrate that to another environment, another cloud environment, or on premise. Your application estate, your application workloads don't really look any different.
Yeah.
Other than some of the so for example, like volumes, you may have persistent volumes that map into particular storage classes that are associated with cloud specific data.
Yeah. So
like EBS volumes or particular types of EBS volumes.
So if you were to migrate from AWS to Azure, those attached storage volumes might appear slightly differently. There'll still be there'll be an equivalent for them, because pretty much all of them have equivalent technologies underpinning them. But the actual detail of the implementation might.
Exactly, and so and Kubernetes does a really good job at abstracting a lot of these things. So you can say in your application pod that I have a volume claim for what I need is a 20 gig volume, and I want the volume to be of a particular type. Now you can define what those types are. So I want a fast disk, or I want a slow disk, or I want a medium disk. And what you do is you then map those types into what that means in your environment. So, a fast disk might be, it might be a local ephemeral storage SSD, or it might be one of the high IOPS versions of EBS. At some point, you've got to decide what those mappings are. But from the application pod perspective, you're abstracting it to a point where you say, I want this to run on a fast disk, or I actually want this to run, it can run on a slow disk. It doesn't matter. But so Kubernetes does a really, really nice job of abstracting quite a bit of the underlying environment, but there are always specific bits. The other one is like load balancers. So, we talked about replica sets. We never talked about how they get called.
How they get load balanced. How that work gets distributed across them.
Exactly. So that's where we sort of briefly touched on services. Now, a service is another type of Kubernetes resource.
Yeah.
But it represents how you can communicate with pods. So you can have a load balance service, which allows you to select the set of pods that are part of that load balance group. If you're running inside AWS, then when you create a load balance service, what it would do is it will automatically create an AWS ELB resource for you to represent the load balance into those pods. Obviously, in another cloud environment, then
it'd be a different technology, and if you were on-prem, it might be something else.
Exactly.
But
it's quite a bit.
Yeah. And treats it the same.
Exactly right. So there's plenty of options for hosting. So as I say, we use EKS. Azure has a hosted Kubernetes service called AKS.
How does that? What are the sort of the main kind of differences and similarities and differences between AKS and EKS?
To be honest, I don't. So I've done quite a bit of Service Fabric, which is another container orchestrator tool on Azure. I've not used their AKS service yet. Although as we've been saying with Kubernetes, and that it's abstraction layers. So all you have to really then worry about from an AKS point of view is, well, okay, so what
What are the quirks?
type of blob storage. We're going to use premium storage for high IOPS, or are we just going to use normal storage for disks, for persistent volumes? Networking is obviously slightly different to AWS. But sort of fundamentally from a Kubernetes perspective, it doesn't really matter too much. Your ops team might have to think about some things, right?
They might care.
Yeah, they might care, but as an application developer, I'm probably not going to really care because I'm just running on Kubernetes, so it doesn't matter whether it's in Azure or AWS. The only thing that I might care about if I'm an application developer, of course, is if I'm running Kubernetes locally.
Yeah.
So if I'm, ideally, so one of the things that we like to do is to make sure that the application that runs on a Kubernetes cluster in, say, the cloud, that a developer should be able to run that entire application on their local dev box.
Yeah, even if they're just running one container of each type, but they
absolutely. So the shape of the application as it runs locally is obviously going to be a lot different. It's not going to necessarily be scaled out to the same level, right? It's not going to
well, a dev box doesn't have to be resilient.
Exactly. So,
but it has to behave the same.
It has to behave the same, but being able to deploy an entire application on your local workstation, I think is a really good practice because then you can do a lot of. So instead of throwing changes over the wall for the integration server to figure out whether it's whether your changes are good or not, because you've run unit tests locally, unit tests have been run by the CI service, but what you want to do is make sure that your changes work from the perspective of integration. You can run end-to-end scenario tests in your local machine. I mean, that's the sort of ideal situation where you can run as much of the quality testing as possible locally, so that it's almost a foregone conclusion when you put it in, through the CI/CD service, that it's actually just going to work because you've already validated it pretty much. Yeah, okay, so there might be some interesting little problems with the fact that it's more of a scaled out service in the cloud and it's running with different networking environment, different storage and so on. But functional changes, they should all be able to be tested locally. And again, because Kubernetes can run anywhere, you can run Kubernetes locally. So there is an option called Minikube, which is designed to make it really easy to run a local Kubernetes.
And that's what our devs use. But also, I know a lot of the other devs that we work with in other organizations. That's the typical one though.
Yeah, I mean, if you're running on a Mac, then Docker provide an out-of-the-box solution now for installing Docker with Kubernetes, which is fantastic. So it's a much more native option of running Kubernetes on your box. You can use kubeadm. kubeadm is all the provisioning tool now for Kubernetes clusters, the official tool, and I've managed to get that working on a local Arch Linux box, on a local workstation. So there's lots of different options for running Kubernetes, which is fantastic because it means you get that sort of that parity of, if I'm running it locally, it's just a Kubernetes workload in containers on a machine. The fact that it's running on one node on a workstation is almost irrelevant to it running in a cloud environment across multiple nodes.
Yeah, that's so. While we're on this kind of hosting stuff, and it's kind of one of the things that for me is a really important one, and that is we talk about availability, scalability, and if we want to be truly available, we need to make sure that we are not just tied down into one availability zone. Different cloud providers do this in different, because some of them, like AWS, have a region with multiple availabilities. The cloud providers straight across region. But effectively, you need to be on data center to make sure that if some contractors dig up the road and manage to slice through the fiber optic cables, then you've still got a service
That's
running.
not as far-fetched as it sounds, is
And
it?
that is not as far-fetched as it sounds, because that has happened.
Exactly, or they go through the power cable, right?
Go through the power cable or go through the fiber optics.
Yeah.
So how do we make our application run across more than one data center?
So you can. So it's about where you. So if you're in the cloud, right? So and you've got availability zones. So each availability zone represents a different data center within the same region. So you can obviously, from a cloud perspective, run nodes, so run VMs in different availability zones. And those availability zones can all communicate with each other over the subnets. And as long as that's the case, then you can run your Kubernetes cluster across those nodes because they're all able to communicate with each other.
Yeah, because typically in a region, you might have more than one data center, but they're fairly close to each other with fast fiber between, so that
close-ish enough so that they've got a I think like having an SLA on the link.
Yeah, but it's
between data centers, so it's really, really tiny.
Yeah, so these not so close that the same event could take them out, but
exactly
close enough that the latency between them is really small.
Exactly. And so as long as you understand, so what you can do with Kubernetes, you can take nodes, so you can actually provide properties on nodes to say, actually, do you know what, that these nodes running in availability zone 1 are different to the nodes running in availability zone 2 to 3. So you can say these nodes are running in these different zones, and then you can make decisions in the pod rules about the pod placement rules for how you deploy those pods across the availability zone. So when you place the replicas, what you're saying is actually place them across availability zones, not just across nodes. So you're getting that sort of resilience across those sort of multiple failure domains in effect. But that's within a region.
Yeah.
Now there is a part of so Kubernetes is a massive project, and there's lots of different strands to it. One of the strands is something called federations. And federations is the idea of creating geo clusters. So you could run a cluster across not just availability zones within a region, but you can actually run clusters across regions. Naturally, there are challenges with that, particularly latency. So if you're running a stateful set.
Yeah, because effectively, if you've got, like you say, if you've got databases, so underpinning it, you've got a database cluster. Let's say, for example, it might be Scylla, and you might have local rights to that, but those rights still got replicated, and so there will be eventual consistency. But the more you go around the globe, you start to run into the fact that the speed of light is the laws of physics apply, and so you naturally encounter those sort of problems.
So you increase your latency. So across availability zones, because you know that there's the links between availability zones are going to be really small in terms of latency. So your consensus ring, in a way, so the quorum, you can make sure that your synchronous replication happens across nodes across availability zones. But from a geo cluster perspective, what effectively you want to do is make sure that your synchronous replicas within your quorum are up to date across availability zones, but that your other replicas that are not part of the quorum, but you still want them to be as up to date as possible to the eventual consistency, may well exist in another cluster. sorry, it's in the same cluster, but in another region.
Another region.
So you're willing to take the latency hit on an asynchronous perspective, but not from the synchronous replica, because when your client, say, inserting data, you don't get a response until all of the synchronous replicas, all the quorum, effectively has said, "I've got the data." So which is really important. If you're waiting, so if the way that the sort of geo cluster is set up and the way that the stateful set is spread across the geo cluster, such that one of your synchronous replicas happens to exist in the other region, then you've got to wait for the latency.
Then your performance is going to tank, isn't it?
It's just going to fall off a cliff. So federations, and federations is really young at the moment. Replica sets are one thing, but stateful sets, I think, have a lot of challenges with geoclustering. Yeah. And it's all to do with latency. And so what you almost want to be able to do, and I don't know whether it does do this because I haven't looked at it in a while, but is to say, actually, for my stateful set, I want all of my synchronous, my quorum replicas to only exist across availability zones within my primary region. But I want to have backup replicas, still part of the consensus network. I want to have backup replicas sitting in my other region, so that should my primary region go down, I have, the log shipping route. I have nearly up to date copy, or up to date if you're lucky, or as nearly up to date as possible within my other region.
And I think we're almost becoming spoiled, aren't we? Because it used to be that to do this stuff, you have to put a lot of effort in, and now we've almost got it out of the box. We're almost like quibbling about,
I know it's a big
that last bit. So I've actually got to do some. I've got to do some work for this last bit. It's outrageous.
Recovery plan, yeah.
Yeah. Whereas it used to be a really, that used to be a really, really tough challenge getting all that done, and now we're almost, like I say, we're almost getting all that out of the box. So actually we're a little bit spoiled in that regard.
It is. I mean, if you think, geo clusters, you've got content delivery nodes, all of this stuff that enables you to run a sort of global operation, and hit, from a CDM perspective, hit your local, the one closest to you. But to have that sort of resilience across a geo level is just amazing. As I say, I've not looked at the Federations project in quite a while, and I know that there were some challenges around stateful sets. I don't know whether any of that's solved yet or not, but I mean, the fact that project exists means that there is definitely a desire to create.
There's a lot of brain power being put towards it.
Absolutely. So very, very fascinating stuff to continue to look at.
So, so to sum up, from just like we've been on quite an arc of a journey. So from the point of view, you write your little application in the container. We can deploy that container in a pod. That pod means that that application can run over machines to make it available, but then those those nodes may then be spread across different availability zones, so different data centers in the same region, and we're almost at the point now where we're going to be able to just say deploy that across different regions and different data centers. So we've achieved almost at the point where we can, the dream of being fully 100% 24/7, almost without having to do it. And as a technology, Kubernetes is an amazing achievement, bringing all that to us. So
it is.
So thank you, Kubernetes. Helped us a lot.
Yeah, it's an amazing technology, really, and certainly seems to be it's now the clear leader.
Yeah, because you mentioned Service Fabric, and there's another one which because obviously Docker, we're trying to push Docker Swarm as well. That seems to be out of favor. Service Fabric seems not be the number one now, so Kubernetes seems, it's looking like that's the way to go, isn't it?
I think so, and particularly, I mean, you look at the proprietary cloud vendor, offerings like ECS, so AWS, ECS. The Kubernetes, I think, there's such an ecosystem now around Kubernetes. There's sort of like a groundswell of people are moving behind Kubernetes. That
Yeah, it took Amazon quite a
already-
while, didn't it? It took Amazon quite a while to.
I think they were the last
Yeah, because
with the managed Kubernetes service.
because they were sort of yeah they were pushing their own Kubernetes service for quite a long time, and it took them a while before they finally crumbled and said, okay, here's our managed Kubernetes. That did take a while to come.
It did, but they've got EKS now. As I said, quite a few updates. It's and as I say, we use it, and at the moment not having any problems. There's only one small issue with EKS that we're waiting for a solution for, which apparently they're working on, and that's to have an individual IAM identity associated with a pod, which you can do in ECS, but an ECS task, but you can't do in EKS at the moment. But I fully expect that to be solved. So yeah, it's that they seem to be fully behind it, and as I say, it's if you're thinking about container orchestration, then these days really you're probably thinking Kubernetes, one and the same. So
fantastic. So I think we are, we're kind of getting to the end of our treatise on Kubernetes. Is there anything else that I mean, there's a couple of things here. Is there anything else that you think we briefly need to touch on this, or is there any pointers for further reading that we should let people
know? So one of the areas that we didn't touch on is packaging your application, which we could talk a bit about briefly. Actually, and we use Helm, so it's the how do you represent your application when it actually is made up of many different types of pod definition.
So if we look at a pod as a microservice, and Helm sort of says, okay, this is all these pods make up my application. This is my overall architecture. Is everything in this Helm chart?
Exactly that. So it's like, well, an application doesn't normally just be one pod. At the very least, you might have a config map, and you might have a service that allows you to address the pod externally, maybe. Role-based access control. We've not talked about the security side of Kubernetes, but you might have specific roles that you want to deploy into Kubernetes. All of these additional resources that all make up the application. So how do you manage all of that? Well, they're all manifests. They're all files. So you can do it. But Helm is becoming sort of think of it as the package manager for Kubernetes manifests. And what you do is you create charts, and the chart represents a collection of Kubernetes resources that get deployed as a unit, as a release. But where also what Helm allows you to do is to template those Kubernetes manifests, so that when you deploy into different environments, you can give those manifest different properties. So like
so you take the same Helm from the Helm chart. Effectively means that you can sort of say, okay, here's my integration environment, here's staging environment, here's production environment, and put the particular tweaks at the right point.
Exactly. So you can say, so you have a values file, just a YAML file, where you can expose properties that you want to allow people to change within the Kubernetes manifest. So, for example, like port numbers or resource limits, or like numbers of replicas and stuff. So you can expose them as individual properties that Helm combines with the Kubernetes manifest through a templating language to produce Kubernetes manifests for that particular deployment, for that release. And it's becoming sort of more the de facto way of deploying Kubernetes applications. So yeah, I mean it's
we will get on to. I mean, one of the things that is in the pipeline for our podcast is, what does our DevOps and deployment pipeline look?
Yeah,
So,
and Helm's a core part of that.
Helm is a core part of that.
Yeah.
But actually, and Helm actually not only is it a core part of that, but it's actually helped us really simplify that as well.
Absolutely, and also people that are building all of these third-party technologies that we're using. A lot of them now are also producing Helm charts to allow people to deploy their technologies onto a Kubernetes cluster. So Helm is a bit like Kubernetes.
Yeah, so it's almost like you've got the recipe ready to go.
Yeah, exactly. A recipe. That's they call it a chart, but it's a recipe, and exactly that. It's rather than trying to figure out how it should all be done yourself, it's people are providing these things out of the box. So it's definitely seems to be the way forward for packaging Kubernetes resources as an application. That's what we do.
Fantastic. So I think we can wrap up here. It's been again, thanks a lot, Paul. It's been an awesome experience just picking your brains on this stuff. It's a massive topic. We'll have to get into security. We'll have to get into networking. We'll have to get into more about our deployment pipeline help. But as a first stab on the subject of Kubernetes, we've covered a lot of ground. So thanks a lot for that, and look forward to the next one. It'll be equally amazing. So
I'm probably just as many poor jokes, right?
Even more. I've only spent 5 minutes working on my jokes this week, and it probably shows. So I might spend even more time working on them for next time. Hi everyone. Thanks for watching this episode. Remember to like and subscribe on YouTube or subscribe on your podcast, and we'll make sure you get every episode as soon as it's released. We're pushing a new episode out every Friday, and so we'll look forward to seeing you then. Thanks for watching. Bye now.